Yes, good morning, students.
Good morning, sir.
Good morning, sir.
Thank you. Okay. So to just to have a recap what we have discussed yesterday, is it possible to say any one of you what we have discussed yesterday? Quickly. Even I will just scroll down. Yeah. Yes, hope remembered this. Hello. Yes, I'm not getting any response. Hope you have remembered what I have discussed yesterday, I'm asking.
Yes, sir.
Yeah. So we have discussed about what? The conversion of the continuous additive weight Gaussian noise channel into a vector channel, right? So basically, I have written the additive weight Gaussian noise model of the channel. I said SI of t is the transmitted signal, and W of t is the weight Gaussian noise, which is usually we consider it will be added to the channel. Then output of the channel will be the what? Received signal, which we denoted by x of t. Right? I said x of t will be equal to SI of t plus W of t. So I call that as equation 1. Okay. And then I said what is W of t, right? So is the Gaussian noise process, and small w of t is the sample function of that. Okay, so this Gaussian noise will have zero mean and a power spectral density of n0 by 2. Then I have written the analyzer diagram, that is x of t, right, which is a received signal which will be passed on to n number of correlators to get back the coefficients, right? So I said pi 1 of t means this multiplier followed by an integrator is known as the correlator. Then output of that correlator, I denote it as small x1, right? Like that up to xn. So I have n number of correlators. Then I said the small x1 or xj is the sample value of the random variable capital Xj. Then I have written which is equal to Si1 plus W or Sij plus Wj, right? So that we have proved. How we get Xj as Sij plus Wj. Okay, see the output of the correlator is the sample value of the random variable Xj, right? So this is what the expression is. Xj is equal to integral 0 to t x of t pi j of t into dt. So I substituted the value of x of t as what? Si of t plus w of t. Then I separated the integration. Then I wrote what is Sij, right? The first term, integral 0 to t Si of t pi j of t into dt is nothing but Sij. And the second term is the Wj. I said this Sij is the deterministic component of Xj, right? Because this Sij is due to the transmitted signal Si of t. Okay, then I said Wj is the sample value of the random variable Wj, that is due to the channel noise. So I wrote Wj is equal to this integral 0 to t W of t pi j of t into dt. So till this we were discussed in the yesterday's class. Okay, so now let me continue with this recap. What to do next? Okay. So it is this topic is slightly based on the random process. So you should have the understanding of probability theory also a little bit. Means that idea should be there in your mind. That only certain things will be clear. Okay. Hope you people have that background because which has been discussed in the previous semesters. So with that understanding, I am continuing this topic. Is that fine?
Yes, sir.
Yeah. 1 minute. Yeah. Yeah. So to begin with, the next is uh, yeah. So okay. So from now onwards, let me consider the new stochastic process. Okay, that new stochastic process is denoted by x dash of t. Yes, sir. Hope I'm audible now. Hello.
Yes, sir.
Yes, sir.
Yeah. Yeah. Let me write that. Consider consider a new stochastic process. A new stochastic process which is denoted by capital X dash of t. Okay, and its sample value is denoted by sample value or sample function, what I can say. Okay, its sample function. So usually what I said, sample function will be denoted by small letters, right? Small x dash of t. Okay. So let me relate this to the received signal x of t. Okay. Which is related to the received signal. So any one of you can say what is the received signal? Yes, what is the received signal with respect to the above diagram?
X
X of
is
t, sir.
equal to SI of t plus W of t.
Yeah, x of t is equal to Si of t plus W of t, right? So what I said, I have considered the new stochastic process. Fine. Sorry. So that new stochastic process, I am denoting it by capital X of t and its value and its sample function by a small x dash of t, right? And I'm relating that to the received signal. So how can I relate that? Any idea? It is like what we have considered intermediate signal. That is while discussing the Gram-Smith orthogonalization procedure, no? I said G2 of t. In the same way, I'm considering here the new stochastic process, which will be denoted by that.
So can you
Yeah,
scroll up a little, sir?
scroll up. Okay. I said, yeah, from this point I started writing today. I said, consider a new stochastic process x dash of t and its sample function x dash of t is related to the received signal. Received signal, that is x of t. Okay, let's write x of t. Received signal x of t. 1 minute. Let me write that here. Okay, received signal x of t. Yeah, I gave a clue. It can be related with respect to that. So I can write if I scroll up, is it fine?
Yes, sir.
Yeah. So I can write x dash of t. Okay. X dash of t will be equal to x of t minus summation j is equal to 1 to n xj by j of t. Xj by j of t. So let me call this as equation 5. Okay. I said I have considered the new stochastic process x dash of t and its sample function I denoted as small x dash of t. I am relating that to the received signal x of t as like this. That is x dash of t is equal to x of t minus summation j is 1 to n xj pi j of t. Okay, so now let me substitute the value of x of t and as well as xj in this equation. I know what is x of t, right? That is my equation 1. And what is xj? Also I know, that is equation 2. Yeah, so what can I write? X dash of t is equal to, yes, any one of you can say what is x of t. Just now you people have said it is. Yes, what is x of t? Yes, I'm not getting any response. What is x of t? I'm asking.
SI of t plus W of t.
Yeah, it is si of t plus w of t, right? Then minus summation j is 1 to n. So what is xj? I can write xj, that is equation 2. Yes, xj is equal to what? Yes, others should respond. What is the value of xj? I derived the expression, right? Xj is what?
Sij plus Wj.
Yeah, it is Sij, right? Plus Wj. This into pi j of t. Right? See, if you know equation 1 and 2, just I'm substituting the value of x of t and xj in this equation. Nothing big I've done, right? So now let me expand this. So x dash of t is equal to what I can write? Si of t, right? Plus w of t, right? Then minus, how can I separate this? I can write summation j is 1 to n, right? Sij pi j of t. Is this fine as one term? Yes, I'm asking, is this fine?
Yes, sir.
Yeah. Then minus summation j is 1 to n. Okay, j is 1 to n. Then Sij, is it Sij? No, it is pi j, right? Yeah. So it is Wj, then pi j. Yes, is this fine? Yes, I'm asking, is this fine?
Yes.
Yeah, now what can I, yeah. So what can I further simplify? So x dash of t, right, will be equal to Si of t plus w of t, and minus, what can I write for this? J is 1 to n Sij pi j of t. Yes, anyone of you can say quickly. What can we write for that? This term. J is 1 to n Sij pi j of t. Yes, people can't say what can we write for this? J is 1 to n summation Sij pi j of t.
Si of t, sir.
Yeah, right. I can write it is Si of t. Si of t, then minus. Similarly, I can write the remaining term. That is what? Summation j is 1 to n, right? Wj pi j of t. Okay. So now this plus Si of t and minus Si of t can be cancelled, no? Can we do that? Yes, can we cancel this?
Yes, sir.
Yeah. With respect to that, can I write x dash of t will be equal to what I can write? It is w of t, right, minus summation j is 1 to n, right, wj pi j of t. So let me call this as equation 6. Okay. Yes, hope it is clear what I wrote for x dash of t, and which is equal to what I can call is means this entire w of t minus j is 1 to n wj pi j of t. I equate it to w dash of t. Is that fine? So w dash of t is that w of t minus j is 1 to n pi j of t wj of t. Yes, hope you people could get this point. So what do you understand from this? Any one of you can say what is your understanding from this x dash of t? I said x dash of t is equal to w of t minus j is 1 to n pi j wj of t, which I can denote it as w dash of t. What is your understanding from this equation? Yes, any one of you can say quickly. Yes, nothing is understood. What I understand from your answer is I feel like that. I took the new stochastic process, which I denoted as what? Capital X dash of t. Right? And I denoted its a sample function as small x dash of t. And I related that to the received signal s of t. Received signal x of t. Right? I said x dash of t will be equal to what I wrote? X of t minus summation j is 1 to n xj pi j of t. So just I substitute the value of x of t and xj, and I came to know that x dash of t will be equal to this w of t minus j is 1 to n wj pi j of t. I am asking you people to just interpret what you have understood from this. Means I wanted to ask you is that this x dash of t, right? What is this x dash of t? Is the sample function of the new random process or new stochastic process x dash of t, right? It depends on what? Does it depends on the deterministic signal Sij, or it depends only on the channel noise? I'm asking. Hope understood my question. Yes.
Sir, it depends on channel noise, sir.
Yeah. So this sample function x dash of t depends only on the channel noise, because whatever the terms I find in this is what only w of t, isn't it? First term is w of t and second term is also related to noise only. So it does not depends on the signal Si of t. Okay. So let me write that. The sample function x dash of t depends only on what? The channel noise. Only on the channel noise. Okay. Only on the channel noise w of t, and not on the signal, Si of t. Okay. Hence, I can write so what can I write? Since x dash of t depends only on the channel noise, not on the received signal Si of t, can I write? Can already I proved that x dash of t is equal to, I said it is w dash of t, right? So I am rewriting the equation 5. Okay, what is that equation 5? Which is x dash of t, which is equal to x of t minus summation j is 1 to n xj pi j of t, right? So I'm rewriting that equation with respect to x of t. Okay, I'm saying what is x of t. From equation 5, so I can write the received signal. Okay, the received signal. What is the received signal? That is x of t, right? The received signal. Yeah, the received signal x of t will be equal to what? Yes, any one of you can say. What can I write for x of t? Yes, I'm expecting you people to say equation 5 I wrote in terms of x dash of t, right? X dash of t is equal to x of t minus summation j is 1 to n xj pi j of t. Now I am asking just to say what can I write for x of t? Means I wanted to represent, because x of t is a received signal, right? So x of t will be equal to what I can write. Yes, hope people are there with me. J is 1 to n, right? Xj pi j of t, right? Plus x dash of t. Is that fine? Just I rewrote that equation 5, right? I wrote summation j is 1 to n xj pi j of t plus x dash of t, right? So I understood what is x dash of t, which is equal to double dash of t. So just let me substitute that. So summation x of t is equal to summation j is 1 to n xj pi j of t plus x dash of t. I said it is w dash of t, and we know what is w dash of t, right? So we put this in a box. Let me call this as equation 7. Equation 7. Okay. So what is this x of t? I said it is the received signal. Okay. So what I wanted to interpret here is the received signal is always a random process. Random process is nothing but a stochastic process. Okay. And that is to be estimated through the transmitted signal Si of t. So which is deterministic, what I can say, right? Yes, hope you're getting what I'm saying. Hello, I said this x of t is what I said. X of t is the,
Random process.
yeah, is the received signal. X of t is the what? The received signal is always, because noise is there. That is why it is it is always a random, is always a random, or we can say stochastic. Is always a random process, right? That is to be estimated, means this x of t to be estimated through the transmitted signal through the transmitted signal Si of t, to the transmitted signal Si of t, and which is deterministic. Okay. Okay, so this equation 7 I said, no? So the expansion of this equation 7, okay, is random due to the what? Because the channel noise is there here, right? W dash of t. So because of this, means the expansion of this equation 7 is a random uh, due to the channel noise at the receiver input. Yet because of this channel noise, and this x of t will be a random or a stochastic, what we can say. Okay, so since x of t is what a random process, means the receipt signal is always a random process. What we need to do, we need to find the statistical characterization of the correlator outputs. So that will be the next topic. Okay, so let us try to understand the statistical characterization of the correlator outputs. Correlator output is what? Xj, right? And it is a random variable, what we have understood. So how do we characterize that? So is there any idea what are the characteristics? How do we characterize the random process? Yes. What values we need to find out? See, characterization of the correlator output. Statistical parameters are what? Mean, variance, and autocorrelation. So these are the three important things which we need to determine. What is the mean of this received signal? Okay, how it is related to the transmitted signal? Then what is the variance? Okay, of the received signal? Then what is the autocorrelation function of the received signal? Then we can say how these parameters are helping in the estimation of the received signal. Okay, means how do we extract the transmitted signal with the random process? Hope I am clear what I am saying. So now let us try to understand the statistical characterization of the correlator outputs. Statistical characterization of correlator outputs. Okay, so let me begin with saying what is, already I said what is capital X of t, right? I said capital X of t is the stochastic process, right? Let me say it is the stochastic process, means random process. Stochastic process. It is also known as the Gaussian process. Okay. Also known as the Gaussian process. And next, what I say? Yeah. Usually I denote small x of t as the what? Sample function. Is a sample function. Okay. In the same way, so let me write, already these things are known. Okay. You have come across these terms. So just I'm again repeating just to have a better clarity. So then let me say what is capital Xj. So this is the output of the correlator, no? And it is the random variable I said, right? Capital Xj is the random variable. Random variable. So usually we call this as a Gaussian random variable. Okay. Gaussian random variable. Just I write in short as RV. And in the same way, small xj is the what? Sample value of the correlator outputs. A sample function of this random variable xj I can write, right? Sample value of the correlator outputs. Okay. So the value of j can vary from 1 to n. Where j is equal to 1, 2, and so on up to n, I can say. Fine. I said no, xj is the random variable, right? So this xj is characterized by its mean and variance, right? I said already the random variables are characterized by its mean and variance. Is this fine? Hence, I say xj means this random variable is xj is characterized by its mean and variance. I hope you all know the meaning of definition of mean and variance. I expect you people to say the definition of what is mean and what is variance. Yes, hope people are there with me. I'm not getting any response. Yes, everybody is there.
Yes, sir.
Hello.
Yes.
Yeah. Yes, I was telling about the random variable xj. I said which is characterized by its mean and variance, right? So similar to that, so let me say wj, okay, capital wj. This is also the random variable. Wj is the random variable similar to xj. So just write in short as rv, right? And it's a sample function similar to what small xj I'm writing now for capital xj. Okay. Similarly, I can represent is a random variable and wj, that is small wj is okay. This is capital wj and this one is small wj, is the sample value. Okay, is the sample value or sample function sample value, right, produced by the jth correlator. Since I'm writing wj, so I can say it is produced by the jth correlator. Okay. How this sample function is produced? This is in response to the white Gaussian noise. Okay, I can say that wj sample value I get at the output of the correlator in response to the white Gaussian noise. In response,
Sir, can you scroll up a little?
yeah, in response to white Gaussian noise. In response to white Gaussian noise, that is capital W of t. Yeah. Yes, is this fine? Just I'm letting what is what. Is this fine?
Enough, sir.
Yeah. I was told capital Xj is what? I said it is the random variable, right? And small xj is the sample value of that random variable. That is the output of the correlator, right? I said that this random variable is characterized by mean and variance. We are characterizing the random variable by its mean, this, and its variance. So these are the two important parameters which we are going to find out for this given random variable. In the same way, I said Wj is the random variable, capital Wj, and its sample value is small wj. So that is due to the what? Due to the white Gaussian noise, right? Hope if I move, is it fine? And similar to, is this fine?
Yes, sir.
So
Yeah.
scroll down.
Scroll down. Scroll down or up? Okay. So similar to this, as I said, how xj is characterized, no, by its mean and variance. In the same way, the random variable wj, the, shall I scroll up?
Yes, sir.
Yeah. Yeah. So the random variable wj, okay, is also characterized by its mean and variance. Okay, this random variable wj has zero mean. Okay, this random variable wj has zero mean, okay, and power spectral density PSD of n naught by 2. So this is by definition, we know this, right? The noise is having a mean of 0 and the power spectral density of n naught by 2, right? This is its mean and it has a power spectral density of n naught by 2. So this is by definition, we can say. By definition of the white Gaussian noise. Okay, so now let us try to find out the mean of the random variable xj. How do we find the mean of the random variable xj? Any one of you can say. So we know what is xj, right? Xj is Sij plus Wj. That relation we know, right? So how do I am asking, how do we find the mean of the random variable xj? Yes, is it possible to say, any one of you? Because already I said what is the mean of this Gaussian noise? It is 0, right? So by knowing that, can I say the mean of the random variable xj depends only on Sij? Yes? Yes, hope you are understanding what I am saying.
Yes, sir.
Only on Sij, because the mean of the Gaussian noise is 0. Since I know xj is equal to what? Sij plus wj. Since the mean value of wj is 0, I can say the mean of xj depends only on the value of Sij, right? Hence, I can write the mean of xj. Okay, so the mean of the random variable xj is given by so usually what is the symbol we use to denote mean?
Mu.
Mu, right? So mu, sorry.
So can you scroll on top, sir? Don't mind.
You want me to scroll up? Huh? Yeah. Yes. Till where, man? I said the random variable Wj has zero mean and a power spectral density of n0 by 2. That is based on the definition of wide Gaussian noise. Yeah. Is that fine?
Yeah, sir.
Yeah. Next is I said the mean of the random variable xj depends only on Sij. Right? So I said, how do I write the mean xj? So I can write, let me use a different color. So mean, I said, something why I'm writing. Okay, mu suffix xj. Hope you all understand this is the mean. Okay, mean of the random variable xj. So which is equal to, usually we use the expectation operator, right? Hope you're all aware, E, right? E of xj we write. Yes, are you aware of this? Yes, I'm asking, are you aware of this? The mean of the random variable is denoted by mu suffix xj, right? We can write this as expectation operator, E of xj, right? So which is equal to what I can write? E of, what is expected value, right? E of what is xj? It is Sij, right? Plus Wj. Just I'm substituting the value of xj, right? And I know what is the mean of Sij and what is the mean of means I can rewrite, so which is equal to E of Sij plus E of Wj, right? And the E of Wj is 0, right, by definition. So can I say mu xj is equal to Sij? Is that fine? Yes, because this value, the mean of the Gaussian random variable is 0, right? So I can write mu xj, that is mean of the random variable xj, is equal to Sij. Okay, so let me call this as equation 8. Equation 8. So in the same way, how do we represent the variance? How do you find the variance of this random variable? So first I found what is the mean. Then I said we need to find out the variance, right? Mean and variance are the terms which we use to characterize the random variable. Okay, is that fine?
Yes, sir.
Yes, I'm asking. Yeah. Then how do we find the variance of the random variable xj? How do we define the variance?
Square root of mean.
Square root of mean. Oh. So then what I get? Sorry, it is coming here. Yeah. Yeah, what you said is it is a square root of mean. Then what can I write? The variance of the random variable xj. Is it possible to say what I get?
Root of Sij.
Root of Sij. Yeah, Anand, na?
Yes,
ಆನಂದ್
sir.
ಏನೋ ಮಾತಾಡ್ತಾ ಇರೋದು.
ಹೌದು ಸರ್.
Yes, anybody else? Yes, I'm asking any one of you can say. Yes, Anand said root of Sij. Anybody else? So nobody. Okay, the variance of the random variable xj, unable to move to the next page. Okay, I think any questions to ask so far? Whatever I've discussed, I will tell the mean because I'm not able to go to the next page. So to write that. If I do enter, it's going to the first page. Sorry. Yes, sir. No questions to ask? Hello? Okay, so let me stop with this. I will continue with the variance. Okay, variance of this random variable xj in the tomorrow. Tomorrow is the first hour, no? So let me do that. So let me just have 2 minutes discussion about your case study and innovative question. Have you thought of anything? Any questions? If you have, you can ask. If you don't have questions, then let me discuss. I will post the material about the case study in the GCR today and about innovative questions. Okay, you can study about this one, band pass signal and band pass system representation into its equivalent complex low pass signal and system. Hope you understand what I'm saying. The innovative question will be on what I said, band pass signal and band pass system representation into its equivalent complex low pass signal and system representation. So I said in that there are 2 ways to represent. One is time domain representation, second one is frequency domain representation. You study on time domain representation because in frequency domain we not much to write, right? It is just taking IFFT and other things. So time domain procedure is important. So study well that. I will frame a question such that you should be able to answer that as your innovative question answer. Is that fine?
Yeah, sir. So you said into its equivalent?
Complex low pass signal and system. That is time domain procedure I have discussed, no man. Band pass signal I separately I discussed, then band pass system.
Got it, sir. Got it.
Then together both signal and system. Right? I said because of the exponential term in the representation of band pass signal and as well as system, its analysis becomes complex. So how do we simplify that? Right? I wrote the diagram at the end. How that in phase and quadrature component with its impulse response, HIFT and HQFT, we are able to get the things, right? Hope got that?
Got it, sir.
Yeah, that you need to write.
Portion is and the
Yes,
portion
ma'am.
is,
Yeah, portion is till whatever I discuss tomorrow.
okay.
Okay, so tomorrow all should attend because tomorrow's topic will be there for the test. Is that fine?
Okay, sir.
Yeah.